Hello, this is Dr. Rahil and we are going to start the new chapter, Synchronization Tool, in this week. And as we know that we have already studied processes in chapter 3, what are the processes and how they are created, how they save the state, and etc. What about the related details about the processes we have studied. And then we studied about the threads, that how multiple threads are actually created, are actually forked from a process. Okay, and then we have seen this CPU scheduling, that how actually CPU schedules those threads and those processes. And there are different approaches we have studied, first come first serve, and different approaches like shortest job first and etc. Okay, so in this chapter we are going to see that how actually what are the actually synchronization tools we have currently, and how the synchronization approaches actually works. Actually we have two type of approaches, we have two type of solutions to synchronization. Before going to that, I must tell you that what is a synchronization. Synchronization is actually in the processes, if two processes are executing, and if two processes are executing, let's say this is P1 and this is P2. If two processes are in execution, then how to synchronize them if the data shared in between them, if the data is shared in between them. So if I suppose this is CPU, and these are two are maybe sharing a common set of data, maybe here they share a data, right? They share a data. Now this data is being updated by one of the process, okay, either by process 1 or by process 2. Okay, so how to manage them for forcing them to execute in orderly manner, right? In orderly manner, so that we can get the result as expected. So to get the expected result, we need the synchronization in between two or more processes. Okay, so we have two approaches. I already told you that we have a hardware approach, and we have also software approach. So in this chapter we will be exploring software approach first, and then we will go to the hardware approach, right? So moving to the chapter, we have here the background, and in background we will see some of the problems we have might already seen while we are studying the processes chapter. If you remember that consumer and producer problem, right? In consumer and producer problem, if one is producing but other one is not consuming, then there is a issue of synchronization, right? So this is a background to create or to motivate towards this chapter, right? Then we will see the main content of this chapter, where we will see the critical section. What is the critical section? Critical section is actually a section where a section may be containing a shared data, maybe file, or maybe a variable, or maybe some database, right? Whatever the information which is shared in between two processes, and both are working. If both want to access this data, then this is called as a critical section. Okay, so there are some problems associated with critical sections, that if two processes approach to a critical section, then how to manage them for orderly execution. There are some solutions, as I have already told you, the software solutions and the hardware solution. We have a software solution here. This is Peterson's solution, is a software solution, and we have also hardware solution, where we have different type of hardware solution, including the locks and semaphore. We have also some memory barrier, and we have also hardware instructions. For atomic execution, atomic execution. Okay, then we will see mutex locks and semaphores. These are two approaches to overcome the situation. Also, we have monitors. Monitors, these are actually supervise. They play actually a supervising role, where they see that if someone has left but forgot to signal the release of resources. It means that whenever a process occupies a resource, shared resource, then it sends some call, it sends some signal to wait for others. But when it finishes its job and it has to release the resource, but it forgot to release. In such situation, this mistake can be a mishap in cluster computing, and it can be a mistake in such sense that as a mishap in such sense that a packet has been dropped, or maybe a mistake by a programmer that he forgot to signal the release of resources. So monitor is very useful in such conditions. Also, we have liveness. Liveness is actually, this plays actually HR role, right? Human resource role, that everybody has some, actually there are some criteria, there are some requirements for synchronization, right? That everybody should be given some time, right? Everybody should progress. Nobody should occupy resources, even if he or she, even if that process is not using the resources. So if it's not reusing the resources, then it has to release the resources. So to manage such requirements, there is a liveness, that everybody should be given some time, right? So liveness, we will see the liveness here, and then in the end we will evaluate those algorithms. Okay, so this is a synchronization chapter, and I must inform you that in this chapter, whatever the topics I cover, if the topic has great importance, I will be focusing more on that, and if the topic is of less importance, then I will be skipping some of those slides or maybe topics, or I may be explaining them explicitly or simply to avoid the bookish details, right? So we'll see here that the inconsistency may occur in the orderly execution of cooperating processes. Cooperating processes means if two processes are cooperating with each other by updating the data to each other to the shared memory, then these processes are called cooperating processes. When we talk about the synchronization, we also call them as cooperating processes, right? So we have a very famous problem of producer and consumer here. As we already have seen that if someone is producing, keep on producing, but consumer is not consuming, if consumer is not consuming those, okay, then this process, there is a synchronization process problem, right? Why? Because this effort of CPU of producing the process can be used for some other process, maybe Pn, right? Maybe can be used for some other process, but it keeps on producing. So if there is a consumer ready to consume this production, then it's fine. But if this consumer is not ready to consume and CPU constantly producing the contents, okay, or maybe the data, or maybe whatever, okay, then there is a problem of synchronization. It's like a market. If you have a shoe shop and you are keep on producing but you don't have such sale, then there is a producer consumer problem, right? So this thing actually leads to the race condition. This condition is actually a race condition. right? Race condition can also be explained in some other ways. For example, if process P0, if there are two processes P0 and P1, they are creating a child process by using the fork system call. Okay, now here come to the picture. We'll be seeing the resource which they are trying to access is next available PID. Now for suppose if consequently if they both try to approach the next available PID on the exactly on the same time, right? On the same time, if these two processes try to approach this next available PID, then what will happen? A new PID 2615 will be returned to both the child of P1 and the child of P2. Both will get the 2615 PID. However, it is expected that both will get different PID. Maybe one will get to 615 and another will get to 166. Okay, 2616. But what happens that a mishap has happened and the time has not been managed properly, and both processes were allowed to access a shared process, a shared memory, a shared data. Then what happens that a mishap has happened. Okay, now this condition is called as a race condition, right? So unless there is a mechanism to prevent P0 and P1 from accessing variable next available PID, the same PID could be assigned to different processes. Now this is just one example, but there are several severe examples, cases are also available where this race condition is very much worse in the process in the CPU scheduling. Okay, what is a critical section? Now actually in previous example the excess of this portion is actually a critical section, right? This section is actually a critical section where both processes are aimed to are actually planted to access for their PIDs. Okay, so this section is actually a critical section. In memory, if we see that, for suppose there's an I variable, okay, maybe I equals to 10, and here's one algorithm, maybe process 1, okay, and here we have process 2, process 1 and process 2. Now if this one wants to increment I, okay, and this one wants to decrement I, okay, this is a critical section problem. For example, this access this, okay, and it will increment this to 11, right, and this will access to this after some time. If this access to this, and then it will be decremented to again 10, so result is 10. However, there can be possibility of another, or maybe we expect that process 1 will process 2, maybe process 2 will be decrementing the variable, right? So what happens that we may expect that 9 is the output, but somehow some mishap has happened, then process 2 has delayed and still we can get the result of 10 here. Okay, so critical section problem is each process has a critical section segment of code, right? A piece of code in a program, let's say this is P1 and here are many maybe line of codes, and there is some line of codes which actually belongs to some critical section. Okay, so this line of code into this block is the critical section, and then the remainder section goes here. Okay, so in almost in every process there is a critical section. Okay, process may be changing some variable, or maybe updating table, or maybe writing some files etc, and this portion is called as a critical section. When one process is in critical section, then no other may be in its critical section. Now I must tell you that there is difference between critical section and CPU access. For example, if I say that I may write here, okay, if I say that a process P1 is executing in its critical section 1, 2 and 3, okay, there are 3 lines of course, and then there is remainder section. Now if there is a flag, let's say that if this is 1, it means that this process is in its critical section, then here flag goes to 0, that this process cannot be entered into this critical section. This is one of the actually solutions of this of solving this problem. Okay, so for example, if this process has priority, maybe priority of maybe low priority, right, low priority task. Now P2 arrives with very high priority, right, and P2 wants to access the critical section. Okay, now P2 wants to access the critical section. What happens that if this is non-preemptive, which means it is non-interruptible, then it's fine. But if it is interruptible, or if it has been interrupted somehow, it has been interrupted because this might have some highest priority and this is very low priority. If this critical section is interrupted in maybe second line of code, then what happened that CPU resources are released. Actually, in this situation, the CPU resources are released. But this critical section is not released because it is still in the critical section. We can see that still there is 1 line of code is remaining out of 3, which means that process 1 critical section has not completed yet. So it means that this process is an atomic process. This is an non-preemptible process. Okay, so you must keep in mind that CPU resources are different. CPU resources are different than critical section. Okay, one might have CPU resources but may not enter into the critical section. Okay, so whenever I'm talking about some concepts, you must keep this thing in mind, that critical section and CPU resources are 2 different things. Okay, now each process must ask permission to enter in a critical section, where we have an entry section, okay, and we have an exit section, and the remainder section goes. As I have already told you that okay, let's see into the next slide. Okay, so the general structure of a critical section is that there is an entry section and there is an exit section. Now if PI goes into the critical section, then this entry section would give a signal of wait to other. Okay, and when this exit from the critical section, then it releases, right, release the resources and signal to the remaining processes about its release of resources. So this is a general overview of the process. Where I must also draw that if this is a critical section, then there's an entry and there's an exit. Okay, so this is in critical section. Whenever we are implementing the critical section, we must have this entry and exit section. This is a protocol. This is a protocol we must follow. Okay, Now there are several requirements of critical section. To address the problem of critical section, we must have some protocols, or maybe we have a set of instructions which should be met, right? So the protocol consists of these three requirements. The critical section problem protocol consists of these three requirements. The mutual exclusive, which means that if one process in its critical section then no other process is allowed to enter. Okay, so this is a mutual exclusive, which means that mutually decided. For suppose P1 and P2 both decides that which one will go first. Okay, if this say that this process will go first, then it will go to the critical section and finish the work, and when it will leave, it signal to this process, then it will come to critical section. Okay, so this is a mutual exclusive, that at a time only one process can be its critical section. Another is progress, that every process must be progressing. For example, if a process is not executing, if no process is executing in its critical section, if there is no process in critical section and there exists some process that wish to enter their critical section, then the selection of process that will enter in critical section next cannot be postponed indefinitely. Okay, you understand that if a process wants to enter into the critical section and no other process is ready to enter into the critical section, even if that process has low priority, it will be allowed to enter the critical section. Okay, so it will not be postponed indefinitely because some other high priority processes are in the expecting to use in the critical section in near future. So this will not happen. The process will progress even if it's low priority process. Okay, another is bounded waiting. This is one of the ethical, actually these requirements are ethical requirements. All requirements are some ethical requirements, that okay, use of mutual exclusion and progress, let other to progress. If you are not using a critical section, then let others to progress, is also ethical bound. Okay, also there is a bounded waiting. Bounded waiting means if a process is entering into the critical section, then then that process must inform that how much time it will take, how much time others will wait until the critical section will be released. Okay, so for example, if a process P1 is entering in its critical section, okay, and a process P2 is waiting, now this enters here and this might take 1 hour, or maybe it lives here forever, right? Forever. Whatever time this process has to take inside the critical section, it has to inform this, that I am going into this critical section maybe for 5 unit of times. Okay, so there is a bounded waiting. Okay, so these are 3 requirements we need to consider whenever we are seeing some algorithms or maybe some hardware or software approaches. So we have some interrupt based solutions. I don't know why the animation is there. Well, we have some interrupt based solution. Very simplest solution to this problem is the interrupt based solution, where we have some maybe if we have this can be actually applicable in uniprocess, when we have one process, okay, one processor, uniprocessor machine. Okay, when we have one processor, then we can disable the interrupt and enable the interrupts, okay, on exit. But this will not solve the problem, because what if the critical section code runs for an hour? Then what will happen? Some process starve and may never enter into their critical section. What if there are 2 CPUs? Now the game starts here. What if there are two CPUs? Now this is okay for maybe a uniprocessor. It may work somehow, it may work up to some extent, but what if we have multiple CPUs, we have multiple threads, then what will happen? So we have some different solutions.